Okay, so we're gonna look at how to draw Lewis structures. What a Lewis structure is or does is it shows us in any molecule, say a molecule of water that we know as H2O. It shows us how those two hydrogen atoms and the one oxygen atom connect. Where are the bonds? Where are any extra electrons? And things like that. So we have these 4 steps here for you, and I'm going to show you a bunch of examples using these 4 steps. You'll obviously want a periodic table for this. That's why that's pictured too. So for our first example, let's actually work through carbon dioxide together. And so our first step says to add up the total number of valence electrons. Now, a shortcut, if you remember, for finding the valence electrons is that it's the same as the group number. So everything in this first column here has 1 valence electron. Everything in this column has 2, 3, 4, 5, 6, 7, 8 valence electrons. The reason we only care about the valence electrons is because we're looking at how certain atoms are bonding together, and that's only going to happen with their electrons in their outermost shell that are most accessible, the valence electrons. So for CO2, we have 1 carbon and 2 oxygens. Carbon, because it's in that 4th column, has 4 valence electrons. And then we have 2 oxygens, because it's CO2, and oxygen has 6 valence electrons. So this, even though a lot of you might be able to do this in your head, this is the type of work I'd want you to show on paper for anything you're doing for this class and turning in. So 6 times 2 is 12, plus 4 is another 16. So that now means that for our Lewis structure, we are working with 16 electrons. It no longer matters that carbon brought 4 and that each oxygen brought 6. All of that's off the table. We're looking at 16 electrons that are somehow going to be used and shared throughout this molecule of CO2. Okay. Our second step is to draw a skeletal structure. So what I mean by that is just kind of a general layout of where's the carbon, where are the oxygens in relation to one another. So we'll always put 1 atom in the center, the central atom, and then everything else will attach to it. So we have the top, the bottom, the left, the right, and that's it. For the central atom, if you have a carbon, it goes in the center. In this case, we do have a carbon. So I put the carbon in the center, and then you can either put the oxygens on the left and the right, or if I wanted to, I could have put one of the oxygens on the left and one on the top, or one on the bottom and one on the top. It doesn't matter, but my carbon's going to be in the center and everything's going to attach to it. If I didn't have a carbon, this is a little bit of a shortcut here, but it works for this class. If I didn't have a carbon, any element that I only have 1 of, that's the one that would go in the center. And again, that's a shortcut if you want to learn more about how you actually figure out what goes in the center in other cases. The topic you'd want to look up is called formal charge, but it's not something we worry about at this level. So my skeletal structure, I just chose to put the C and then the O on the left and right, but it doesn't matter. Next step. Connect the peripheral atoms, so the ones on the outsides of the carbon, that's all it means by peripheral. Connect the peripheral atoms to the central atom using single bonds. So a bond, I'm going to draw like a line. A line is a single bond. If I were to draw another line, that'd be a double bond. Another line would be a triple bond, but we never go beyond triple bonds. So boom, right there, I've drawn 2 single bonds from each carbon, or from each oxygen to the carbon, from the oxygen to the carbon. That's how, because they have to be connected. So if this is one molecule, I know everything has to be connected to that central atom. Then it says use up the rest of your electrons as either bonds or lone pairs until every atom is happy. Now there's a lot to unpack there. These single bonds that I drew in pink, each of those bonds contain 2 electrons. So bonds, which we draw as lines, contain 2 electrons each. So of my 16 electrons, I've used up 2 here in that first bond and 2 there in that second bond. I've used up 4. So 16 minus the 4, I now have 12 electrons that I still need to place somewhere in this picture. I can place them as bonds, or I can place them as what are called lone pairs. A lone pair is 2 dots, and that also represents 2 electrons. And so currently I have carbon single bonded to each oxygen. I still have 12 more electrons I need to use of my 16. Now, what does this mean until every atom is happy? That's obviously not formal language, but generally we're looking at having complete full outermost shells, which means 8 valence electrons. So there are some exceptions we'll come back to, but for the most part, we want every atom to think they have 8 electrons. Now, electrons are being shared in this process, so sometimes I'll show you how the electrons can kind of double count for different atoms, but we want each atom to think they have 8 electrons. Looking at what we have so far for carbon dioxide, I've used up 2 4 electrons. I need to use up a total of 16. So for now, I'm not going to overthink it. I'm just going to throw the rest of my electrons in there as lone pairs. That's my choice. Have an eraser handy. So 2, 4 from the bonds that are there, 6, 8, 10, 12, 14, 16. So I have 16 electrons in this picture. That's great. I need to make sure I keep 16 electrons in this picture. And you'll notice of the oxygen, I put some lone pairs on the top, the bottom, and the side. Think of every atom as being like in a box where you have a top, a bottom, a left, and a right. And on each of those places, you can put bonds or a lone pair. So looking at this, I've used up all of my electrons. Use up the rest of your electrons. Check. But now we have to check that every atom is happy, every single one. Looking at first this oxygen, that oxygen that I circled in blue. It has 2 electrons on top, 2 on the side, 2 on the bottom, and it thinks it gets both of the electrons that are hidden inside that bond. So 2, 4, 6, 8, that oxygen is happy. It has a complete octet, a full outer shell. Let's check the carbon. The carbon also, everything that's touching it, it's 4 sides. It has the 2 electrons on top in a lone pair, the 2 electrons on bottom in a lone pair, 2 on its left in a bond, 2 on its right in a bond, 2, 4, 6, 8. The carbon is happy. Check the other oxygen. It has the 2 electrons on top in the lone pair and the 2 electrons on the left in the bond. That's only 4. That oxygen is not happy. Now, I can't just go and give it 4 more dots because then I'd have more than 16 electrons in this Lewis structure, in this diagram. So at this point, all I can do is choose to rearrange. Whenever you have like a situation like this where oxygen's not happy, but I can't just, if I just moved one of the lone pairs from carbon over to oxygen, like that, well, now my carbon's not happy. Now my carbon only has 2, 4, 6 electrons. So moving a lone pair isn't going to work in that case. However, instead of when I remove the lone pair, one of the lone pairs off of carbon, I can choose to redraw it as a bond. So now that's a double bond in between the carbon and the oxygen on the right. Now my carbon, if you check it, is still happy. My carbon still has 8 electrons. 2 in the bond on the left, 2 in the lone pair on the bottom, and then another 4 because of the double bond on the right. My oxygen is closer to happy than it was. It only had 4 before. Now it has 2 on top and then 4 because of the double bond on the left. So now we're closer to happy. If I do that same thing again, take another lone pair away from carbon, and give it to the oxygen as another bond, as a triple bond. Now if I check, we have 2, 4, 6, 8, 10, 12, 14, 16 electrons in my picture. That's great news. Then we need to make sure that every atom is happy. This oxygen has 8. The carbon has 8. The oxygen has 8. So by everything I said in step 4, we should be good and done. However, it's just a little weird that there's a single bond and a triple bond. If we can make them the same, we should. That only applies for if it's like, in this case, it's carbon attaching to two oxygens. So you'd think they would interact in the same way because they're both oxygen. If one were oxygen and one were something else, I'd be way less concerned about trying to make them even or symmetrical or matching. So how could I make these the same on each side? Let's just try messing around with it. Again, have an eraser present. So I took away one of the bonds, one of the triple bonds, and I'm going to make it so they're both double bonds. So by at least just moving those electrons, I know there are still 16 in my picture. The problem is now, this oxygen only has 6 electrons, and this one has 10. So they both aren't happy. But what I can do is then move one of the lone pairs. It doesn't matter which one. I can then move one of the lone pairs from one oxygen to the other. And again, I'm showing you it doesn't matter about left, right, top, bottom in terms of where I put those lone pairs. I think I'm done. At the very end, you should always know if you get these right or not, because you should be able to check, do you have the right number of electrons in the whole picture? And is everyone happy? Does everyone think they have 8? And that is the case here. Before we look at a bunch more examples, I want to tell you about the exceptions to this every atom being happy thing. We had said that every atom wants 8. That's a full outer shell. Some exceptions you need to know. Hydrogen, beryllium, boron, and aluminum. These ones, to be happy, don't need 8 electrons. Hydrogen only wants 2 electrons. Beryllium wants 4. Boron and aluminum want 6. So when you're going through your Lewis structure and you're checking, is everybody happy? For these ones, you're not trying to get to 8. Let's look at another example. For instance, CH2O. So step 1, adding up our total number of valence electrons. Carbon is in the 4th column, so it would have 4 valence electrons. Then we have 2 hydrogens. They're in the 1st column, so they each have 1 valence electron. And we have 1 oxygen, it's in the 6th column, so it has 6 valence electrons. That would give us 12 electrons that we need to use in this Lewis structure. For drawing my skeletal structure, I have a carbon, so it's going to go in the middle. You can put a hydrogen on the left, a hydrogen on the right, top, bottom, doesn't matter. And you also need an oxygen. So we're not doing any long lines, long strings. We need everything to connect to the central atom. So that would be a reasonable skeletal structure. Then we want to do step 3, connect the peripheral atoms to the central atom using single bonds. 1, 2, 3. Now we just need to use up the rest of our, in this case, 12 electrons. So we've used 2, 4, 6. I need to use 6 more to have used 12. 2, 4, 6, 8, 10, 12. Maybe you tried putting them somewhere else to start. You'll get a feel for where the right place to put them is the more you practice, but just be willing to erase and you'll be good. So I have 12 electrons, but I need to make sure everyone's happy before I decide if I'm done. So this hydrogen only has 2 electrons in that bond, but remember, hydrogen's one of my exceptions, so that's good. Hydrogen only wants 2. Same with this hydrogen. It only has 2, it only wants 2. Oxygen here has 2, 4, 6, 8. It's good. But, and let me clear this up so you can see, let's look at the carbon that's in the center. This carbon only has 2, 4, 6 electrons. Not happy. I can't just draw 2 more on it because then I wouldn't have 12 electrons in the diagram. I'd have 14. So what am I going to do? I'm going to rearrange. I'm going to take one of the lone pairs off of oxygen and I'm going to redraw it as another bond between the carbon and the oxygen. Now if I check, I still have 12 in the picture. 2, 4, 6, 8, 10, 12. Hydrogen is happy, it has 2. Hydrogen is happy, it has 2. Carbon is happy, it has 2, 4, 6, 8. Oxygen is happy, it has 2, 4, 6, 8. Another example, let's look at HCN. HCN, hydrogen is in group 1, so it has 1 valence electron. Carbon is in group 4, so it has 4 valence electrons. Nitrogen is in group 5, so it has 5 valence electrons. That means I have 10 electrons to work with in my diagram. I have a carbon, so it's going to be in the center, and I'm going to attach the H and the N to it. If you wanted to put the H or the N on the top or the bottom, again, that's fine. I start with single bonds. That's using 2, 4 of my electrons. 6, 8, 10. Hydrogen only has 2, but it's an exception. It's happy with 2. Nitrogen has 2, 4, 6, 8, the 3 lone pairs and the bond, so it's happy. But my carbon only has 2, 4, 2 in each bond, so it's not happy. I can't add any more electrons because I'm maxed out at 10 here. But what I can do is take some of the lone pairs from nitrogen. Oops, sorry about that. And move them to be a bond so that the carbon and nitrogen are sharing more of those electrons. Now my carbon has 6, 2, 4, 6 in the different bonds. If I do that one more time, take one more lone pair from the nitrogen, I will be able to make a triple bond. That's the most we ever get. And now if you check, we still have 10 electrons. Everyone's happy. That's my answer. Okay, looking at another one, something like N2. Counting up my total number of valence electrons, I have 2 nitrogens. They're in the 5th column, so they each have 5. That means I have 10 electrons to work with. Now, drawing a skeletal structure, I only have 2 atoms. There's not going to be one in the center. I have an N and an N. Or I could put it on top and bottom. There's no central atom in this case when there are only 2 atoms, but that's okay. That's the only way to lay them out. 2 nitrogens that are going to connect to each other. So starting to use those electrons, trying to get each nitrogen to think it has 8. 2, starting with a single bond to connect them in the first place. 4, 6, 8, 10. I went about it with some symmetry. The problem is, regardless of which nitrogen you look at, it only thinks it has 2, 4, 6 electrons. So that means I need to do more sharing than I'm currently doing. So getting rid of a lone pair and redrawing it as another bond, that at least helped the nitrogen on the right, because now it has 2 electrons on top as a lone pair, 2 on bottom, and then another 2, 4 in the bond. So 2, 4, 6, 8 electrons. That one's happy, but the one on the left still only has 6. So if I take another lone pair from the nitrogen on the right and add another bond, now I still have 10 in my picture and each nitrogen thinks it has 8 electrons. Let's look at O3. So counting up my total, I have 3 oxygens. They are in the 6th column, so they have 6 valence electrons. I'm dealing with 18 electrons. Now this is all oxygen, but unlike that last example of N2, I have 3 atoms, so I can put one of them in the center and have the other 2 attaching to it. I do have a central atom here. Using up 2, 4 electrons to start, then 6, 8, 10, 12, 14, 16, 18. If I check, the oxygen on the left is happy, 2, 4, 6, 8. The oxygen in the middle is happy, 2, 4, 6, 8. The oxygen on the right, not happy, 2, 4, 6. I can't just draw 2 more electrons on it or I would have more than 18, but I can get it to share with the oxygen next to it. So taking a lone pair off of the oxygen in the center and making a double bond between the 2. Now I still have 18 electrons in this picture, but every oxygen is happy. You might be wondering, but they're both oxygens and one has a single bond and one has a double bond. There's no other way around it in this case. So on the first example I did in carbon dioxide, we were able to make it so they both had double bonds. In this case, I promise, no matter how much you try, it's not possible. There's always only one correct way of drawing a Lewis structure. Like, I don't care if your double bond was on the left and mine was on the right. The only way of drawing O3 so everyone's happy and there are 18 electrons is if one of the oxygens is single bonded and one of the oxygens is double bonded. There's no other right way. And so that's going to have to be okay.